Hello everyone, welcome to the AI loop. Today we're going to be talking about positional encodings. The main things we need to look at are what are positional encodings and why do they make sense, especially in the sequence to sequence generation tasks. So let's start. Let's say I give you a sentence like I repeat things. Let's consider this sentence 1. And now this sentence makes sense. I repeat things as a human makes sense. Now let's say I give you another sentence which says things repeat I. At a point without context, this wouldn't make sense, but also generally this is not a grammatically correct sentence. So when we look at sentence 1 and sentence 2, what is it that we get? We understand that the position of a particular word in the sentence really makes a difference and adds to the semantic of the sentence. So this makes us realize that position of the word is a vital thing, that what forms this meaning of a particular sentence. So this really is the intuition behind why positional encodings are vital in transformers. Now let's look at this in the context of transformers. Now let's say we have a transformer block here and we're passing sentence A and expecting an output B. Let's say A and B are two sequences. So this is a sequence to sequence generation task. Now let's say I have the sentence I just ate. So the way transformer works is that initially when you have the sentence I just ate, we can't pass it into the transformer block as a sentence itself. We have to convert them into numbers. So what we do is we get three vectors. Three vectors, each vector representing a word. So we have one vector here, and one here, and one here. Now these vectors are representation of each of the word. I just ate. So now this is a very different thing of how these vectors are formed. So these are learned embeddings. So look at it, just look at it as a way that these embeddings are a very good representation of this particular word. Now from the previous example, we did understand that just knowing the words does not fully satisfy the semantic responsibility, but we need to add that position. We need to know at which position that particular word is in the sentence in order to make complete sense out of it. And it is for this reason what transformers usually happen. What really happens in transformers is that we add an additional embedding. So we have three additional embeddings. Now initially, if you see, these are the initial representations and these are the positional embeddings. Now when we look, these vectors will be added. As a result, we have three vectors which are a very good representation not only of the semantic nature of that particular word, but also they reflect the position that word is in the sentence. Now, why do we do this in transformers? Well, before transformer, if you're aware of recurrent neural networks, what really happens in there is that when we have like a sentence, let's just consider this sentence, when we have a sentence like this, what really happens in recurrent neural networks is that the words in the sentence are passed one by one. So first this vector is passed into the RNN and this and this. So when the words are passed sequentially, it's really easy, or like the model can make a sense out of the position of the embeddings or the position of the words. Now what really happens in transformers is that all the three words are being passed into the transformer at once. Now this really boosts the speed and time at which we train the transformers. But the disadvantage is that when we're passing everything at once, the transformer cannot really make a sense out of the position as to what comes first and what comes last, or what follows one word. So by adding these positional encodings, we're really giving the transformer a hint about the positions and adding a very meaningful representation to the vector. Now, where do we get these positional encodings from? On the base level, they can be learned, but one way they do is that, now let's not get into that part. The way they do is sine and cosine function frequencies. I'll be covering that in another video, but think of it like this. Let's say we have, let's just say we have 4, where it's like 0, 1, 2, 3, and let's just say this is like a vector, okay? Like everything on the right is a vector, and everything on the left is the index. And everything on the left is an index that corresponds to the position of a word. So when we have I just 8, I can represent I as the 0th word, and the index for just would be 1, and for 8 would be 2. So what in the transformer paper that's proposed by Google researchers, what really happens is that after the initial representation, we grab the index of this particular word and we find the vector that's corresponding to that particular index, and we take that vector and add it to the thing. So this is how we're getting the positional encodings, and the way this vector is formed is from the sine and cosine frequency. Now that I'll be covering in another video, but this is how the positional encodings work, and this is why it makes sense, because we're giving transformer a hint about the position of every word in the sentence. Now in a transformer, usually we have an encoder block and a decoder block. Sorry for the drawing again. So usually what happens is, here is where we pass the encodings, and really in the training stage, here is where we pass the output things. So the positional encodings are added at both the stages. So that's it about positional encodings. I hope you liked it. Thank you for tuning in.